Hello friends, welcome back. The next few lectures are going to be on what is known as the theory of learning. Okay, interesting theoretical topics. And today's lecture, I plan to give an overview and lay the roadmap for what's going to follow in the next few lectures. Okay, on the theory of learning. The theory of learning, you could say, focuses on two primary questions. Okay, the first question is what is learning? Okay, and secondly, is learning possible? Okay, now a lot of attention is devoted to finding better techniques, finding better algorithms, and so on for solving real life problems, right? I mean, that's what AI does. But people have also invested efforts in sort of trying to address the underlying question about what exactly is learning and is learning possible at all. Okay. As you may guess, the answers to these questions are not straightforward. And that's the reason why we need a few lectures to cover these topics. What makes it even more interesting is the fact that the answers to these questions, what is learning and is learning possible, will evolve over the course of the next 2, 3, 4 lectures. Okay, so I mean, we are in for a pretty good ride. Okay, where are we in our trajectory of this course, right? I mean, this is lecture number 8, and let's sort of see where we are. What we have done so far is looked at the problem of binary classification. Okay, we have looked at the problem of regression. Binary classification was the problem where we had to classify an input into one of two categories. Okay, and that we did on the basis of training data. Regression was the problem where we had to predict the value of an input based on the training data that we had. So we looked at binary classification and we looked at regression, and we also looked at techniques to solve these problems. In particular, we came up with what is known as a binary linear classifier, okay, and we studied linear regression. So we looked at binary linear classifier, okay, and we looked at linear regression, okay. The linear models were simply one type of models or one type of technique to solve these problems. And we went over them in great detail. We understood how to formulate these problems as optimization problems and how we could determine the best binary linear classifier or the best linear regression model, right? So this is where we are. Now, some of you may wonder, I mean, if we are going to be asking fundamental questions such as what is learning and is learning possible, shouldn't those questions have been asked right at the beginning of the course rather than after we have covered a few techniques and a couple of problems in the course anyway, right? I mean, we've already seen that given training data, you can build a binary linear classifier which will give you some indication of how unseen inputs can be classified or how you can predict a value of a future input. I mean, we have seen how these techniques work. So isn't it a little bit late in the day after we have studied these techniques to ask the question, what is learning and is learning possible at all, right? The reason for this particular sequence, I mean, the reason for introducing the theory of learning after having learned about classification and regression is because we are going to lean heavily while we describe the theory. We are going to lean on what we have done during the binary classification and regression lectures, okay? Because I want to illustrate some of the concepts in the theory of learning with what we have already learned. And if we had not seen a binary linear classifier or a linear regression model earlier, you would sort of be, wondering in a vacuum of what we are talking about. So theory is best learned when you can correlate it immediately with some practical manifestations of that theory. That's the reason why we studied binary linear classification first. We studied linear regression. We looked at techniques to solve these problems. And now we are addressing a more fundamental question of what is learning and is learning possible at all. So that's the reason for sort of sequencing these lectures in this particular manner. Okay. Now, some of you may also have the question, is learning possible? Is this a relevant question at all? I mean, why do we need to even answer this question? Because we have repeatedly said that AI deals with practical problem solving. Okay, we draw on theory from various other disciplines like statistics, calculus, linear algebra, probability theory, numerical analysis, etc., etc. I mean, we have used all of these when we talked about the linear classification and the regression problems. And if AI is only about practical problem solving while leaning on ideas from all of these disciplines, why do we even have to ask the question, is learning possible? I mean, the proof of the pudding is in eating it. We apply these techniques. If we get good answers, sure, we are happy about it. If we don't get good answers, we move on and try another technique, right? So why answer this fundamental question of whether learning is possible at all? Okay. This could be a valid question. And as a corollary to the first point, I mean, if AI is only about investigating different techniques, their improvements and refinements to get better efficiencies, etc., etc., perhaps we don't need to wonder whether learning is possible or not in a theoretical sense. We just focus on solving the problems and, not worry about whether there is a grand theory behind all of it. That's a valid approach too. And I mean, a lot of online courses or some of the college courses also do not delve into the theory of learning at all. Okay, because it's an argument people make that you do not need to concern yourselves with the theory of learning. What you really need to concern yourselves with are techniques, better techniques to sort of engage in problem solving. Okay. However, I do personally believe that it's very, very important to understand the underlying theory and understand how these concepts or ideas have evolved. Okay. And let's see why. Well, firstly, the answer to this question, is learning possible, isn't a simple yes or no. It's not a yes or no answer. And in a way you can say that is what makes the question relevant. Right? If it was a simple yes or no answer, you would say, hey, I mean, you wouldn't need 3-4 lectures to sort of answer that question. So it is not a simple yes or no. And to me, that is what makes the question relevant. We will need to understand the context in which this question can be answered. Okay, so there are certain scenarios in which this question can be answered, certain scenarios in which this question cannot be answered, and we need to understand the context in which this question can be answered. That's very important. Thirdly, trying to answer this question will also tell us what are the conditions that can lead to better learning? Okay, so when we look at the theory, we also understand what it is that we need to do to create the conditions that lead to better learning. Number 4, there are always trade-offs, right? I mean, we've seen trade-offs in virtually every scenario. And what are these trade-offs at a conceptual level? That's very important to know. Okay, so the trade-offs at a conceptual level, you will always make trade-offs, and what these trade-offs are is something that you need to have a very good handle on. So therefore, I feel that answering these questions, what is learning and is learning possible? Answering these two questions is extremely important. Okay. And I think it's worth spending a few lectures on this theoretical topic. So that is what we are going to do. Hopefully I have convinced you that it is worthwhile spending time on the theory of learning and on trying to understand the big picture, the big theoretical picture, right? So let's get started. What is learning? This is a diagram that we have seen before, and our definition of learning to begin with is as follows. Learning is using a set of observations to uncover an underlying process. So what does it mean? There is a physical or any other type of process that is unknown, and you do not, it's unknown in the sense you do not know what that process actually does. However, what you have are examples of inputs and the corresponding outputs of that process. Okay, so you have these input output combos that this process has generated, and the process of learning is using these input output combinations, training data as we called it, to uncover or model the underlying process. Model the underlying process meaning to determine what that process actually looks like if it creates these input output combinations, right? Learning leads to the ability to predict outputs on unseen inputs, right? So the whole objective of modeling the underlying process is to be able to predict the output on inputs that are not a part of the training data, right? So the way things go, as we saw in the binary linear classifier or the regression model, is you begin with training data. On the basis of that training data, the AI model learns, okay? And then when you give it a test input, the AI model, based on the whatever learning it has undergone, predicts the output on this test input, right? So learning leads to the ability to predict outputs on unseen inputs. This is what learning is. This is the definition that we have assumed in the class in the prior lectures, and this is the definition that we will begin the next few lectures with. So this is our starting point for our definition of learning, and this definition will evolve as we go along. Okay, so I hope everybody is familiar with this definition. We've seen it before. Okay. What can possibly go wrong? I mean, at a certain level, even in terms of the problems that we have seen, I mean, the whole idea seems fairly straightforward. Create a model, assume a model, use the training data to find the model parameters. That's called learning. And once the model has been trained, once the model parameters have been determined, use that model to predict future, to predict the output on future inputs, right? Fairly straightforward. What can possibly go wrong? There are a number of things that can go wrong. So let's understand very carefully what can possibly go wrong. Okay. The underlying process is genuinely unknown. Okay. That underlying process is genuinely unknown. What it means is that you know nothing about the underlying process that generated these examples. Okay. So for example, if you were using a regression model to predict the stock prices of a particular stock, you have absolutely, I mean, some of the data is not even available to you, right? The future data is not even available to you, and how this process is going to behave on unseen inputs is something that you don't absolutely know. So you have to spend a moment to understand what this means. And the underlying process is genuinely unknown. And as a result of that, this whole assumption that we made, training data representative of overall data or test data, is an assumption that may not hold. Okay, so what does that mean? I mean, so far we have been saying, I mean, even the resume filtering example that we took, we said that there are 500 resumes that you have to process. You pull out 1,000 of them randomly, use them to train your model, and then run that model on the remaining 4,000 resumes and predict whether you're going to sort of shortlist that candidate or no. That's not how it works in many real life problems, right? I mean, the entire data is not even with you. So to say that the training data you have is a representative of the overall data, it simply doesn't make sense. If you don't have the overall data with you, if some of the data is going to be generated in the future, clearly what you have cannot be a representative of what is likely to happen in the future. So training data representative of test data, this is an assumption that we have been making. This assumption may not hold. Okay, so you have to understand this, you have to accept this fact, and this flows from accepting the fact that the underlying process is genuinely unknown. Okay, so when the underlying process is genuinely unknown, your training data, which is what you have, may simply not be entirely representative of all data, right? And in many problems, the training data is also a very small fraction of the overall data. So for example, consider these guys who predict elections, right? Polling experts. They poll, like 500 people or 1,000 people and predict the election outcome in a constituency that has millions of people. Now, clearly the sample set, the training data that they have is a very, very small fraction. So to assume that training data covers the entire real data is not fair. And that is the reason why many pollsters often get their predictions wrong. The data they have is simply not representative of the overall data. It's a very, very small fraction of the overall data. So this assumption, this is one thing that we absolutely need to be clear of. And this is the first point in my slide, which is titled, what can possibly go wrong? So the first thing that can possibly go wrong is that your training data is, number one, extremely small fraction of the overall data, and it may not be a representative of the overall data because the underlying process is genuinely unknown. Okay. I covered this. Training samples may not be adequate, and that leads us to the question, how many do you need? So if you are trying to train an AI model, how many training samples do you need? I mean, this is a question that emerges from the observation that training samples may not be adequate. This is the second thing that you can that can go wrong. The data that you have may not be adequate. Okay. Patterns in full data may not be captured in training data, and patterns which are not in the full data may be reflected in the training data. Clearly, if you pull a small sample out of a large sample of data, the smaller set may not capture all the patterns that exist in the entire big data, right? Conversely, just coincidentally, the training data that you have plucked may have certain patterns that are not really, which really don't exist in the overall data. So this could work both ways. And AI models are about capturing the underlying patterns in data, right? So your training data may actually not capture the patterns in the full data, and conversely, your training data may have patterns that don't exist in the full data. So this is another thing that can go wrong. Okay, how seriously should you take the training data? Should you capture every pattern that you see in your training data? This is a very, very important question, and I think this question is really goes to the heart of what we are going to be studying in the next few lectures. How seriously should you take the training data? Do you take it as the gospel? Do you believe that it totally represents the bigger data set, the bigger data set that you have not seen? Or should you just sort of take it as indicative of the overall data? I mean, how seriously should you take the training data? Very important question. And finally, there is noise. I mean, this is an aspect that we are not going to really deal with, but the same input may give different outputs if your process is noisy. Okay, noisy in the sense it introduces an element of randomness in the output. And if that is the case, clearly your algorithms are going to struggle, right? So these are some of the things that can possibly go wrong. I want to illustrate what we just the points that we went over with some examples. Okay, I want to illustrate with some examples. Let's see this. Okay, in the last point about noise, I hinted at this fact, but a random process cannot be learned. Now this you will accept. If the process that you have that maps an input to an output, let us say is a random number generator that totally disregards the input and just keeps spitting out random numbers, that's a process that you will not be able to learn, right? So random processes cannot be learned. We just give up on random processes. There's one example of what can go wrong. If your input output process has an element of randomness in it, that's not something that you're going to be able to learn. Okay. Here is another example I want to show you to illustrate what can go wrong. I mean, I'm giving simple examples, but you should hopefully they help you form an impression of what can go wrong. So these are inputs, okay? These three inputs in the first row, they yield an output of +1, okay? These three images, 1, 2, 3, 1, 2, 3, yield an output of +1. This is your training data. Suppose you are given this training data, and inputs 4, 5, and 6 yield an output of -1. So your training data has 6 samples. This is the training data. Okay, input output pairs. This is your test input. You are required to predict on the basis of training data. Okay, this is the test input. What will be the output for this particular image? Now you can spend a moment, you can pause the video. I encourage you to pause the video and look at these examples and come up with an answer. Okay, so go ahead, pause the video. Okay, I'll move on. Some of you may say that the output corresponding to this input should be 1. Okay, and why would you say that? You would say that because you would observe that the top left, if the top left square is black, as it happens to be in this test input, the output is supposed to be 1. So some of you will say that the output is 1. Some of you will observe that patterns 4, 5, and 6 are actually symmetric. They have an axis of symmetry. Okay, so for 4, this is the axis of symmetry. For 5, let's say this is the axis of symmetry, vertical one. For 6, the horizontal one is an axis of symmetry. And because this figure is symmetric, the output should actually be -1. Okay, so some of you may say that the output for this particular test example should be +1, and some of you may say that it should be -1, right? So the training data may not be adequate to tell you what the output should be. This is an example of something that we discussed on the earlier slide. Your training data may not be adequate. Okay. Another example, let's say you have a process which gave you the following input-output combinations. When the input was 1, the output was 2. When the input was 2, the output was 4. When the input was 3, the output was 6. And let's say the test input was 4. And what was the output? You were asked to predict what the output would be. Now, many of you will naturally predict that the output would be 8, right? Because you can sort of see that y is 2 times x. What if I told you that there is another equation that these points satisfy? If you look at the above data also satisfies the equation y equal to x cube upon 2 minus 3x square upon 2 plus 3x, right? And if you sort of used this as your model, you would get a different answer. You would not get 8. What you would get is 64 upon 2, which is 32 minus 48 upon 2, which is 24, plus 12, right? So this is equal to 20. So is the correct answer 20 or is the correct answer 8, right? So now some of you may say that, I'm sort of trying to trick you by giving you only partial data. If I gave you lot more data, you would be able to tell me whether this is the correct equation or whether y equal to 2x is the correct equation, right? Which of the two are the correct model. However, it is a fact that even if I give you 100 data points, you will always have this possibility of creating an even higher order polynomial that satisfies all the conditions of your 100 training data points, and which is different from, you can have multiple. What I'm saying is that you can have multiple higher order polynomials that fit 100 training points, 1000 training points, and so on and so forth. So more data points simply may not be an answer, because even in the case of 100, 1000, 2000, 1 million data points, you can always find multiple higher order polynomials that satisfy that data, right? So this is an example of what can go wrong. Hopefully you're able to see. In the previous example, you thought that the number of training points was not enough. In this example, I'm trying to demonstrate that, the number of training points is not an issue, because things can still go wrong. Okay, here is an even more tricky example. Let's say you are concerned with the problem of binary linear classification. And this was your training data. The yellows were class 1, the blue were class 2. And I want you to ignore the red dots for a moment. Okay. And let us say you created a really good classifier, or what you thought was a really good classifier, which created a decision boundary like this, right? I mean, a very sophisticated classifier which created a boundary like this. Okay, you get the idea. You get what I'm trying to do here, right? I am trying to take this training data very seriously, okay, and create a boundary, create a classification boundary which works very well on the training data that we have been given. Okay. But assume that now assume that the red points that I have shown you are actually yellow. Let's say in your test data, the red points that I have shown here are yellow. You would clearly, although you are not making any mistake on your training data, you would start making a lot of mistakes on your test data. And it's not inconceivable. I mean, in this data set, it's not inconceivable that the red points could be yellow, right? I mean, the red points are not way out there. They are not over here, right? These red points could conceivably be yellow in your test data, right? And in which case you are going to end up making a lot of mistakes. Whereas your training on your training data, your model efficiency was 100%, right? So this leads to this question that I asked: how seriously should you be taking your training data? I mean, is it simply better to create a decision boundary like this? I mean, we create a decision boundary like this with the notion that yes, I may make some mistakes on my training data, but my test results will not deviate significantly from my training results, right? So this right here, you can see some of the challenges, some of what can go wrong with creating decision boundaries that are extremely accurate on your training data, but could do badly on your test data, right? And like I said, you have to ask the question, do you want to take a hit on your training data and create a boundary that will work equally well, make a roughly similar number of mistakes on your test data as well, right? Or do you want to create a polynomial? I mean, like a parabola type of a thing. I mean, what makes sense? I'm trying to illustrate what can go wrong. Okay, it's not as simple as creating a training or the problem of classification, or in general an AI problem. There are nuances to it, and what I am trying to demonstrate is one struggle that you have to deal with is how seriously you take the training data. And this is an illustration of what can go wrong if you try to attain 100% efficiency on your training data, right? So now already you don't know what you're supposed to be doing here. Great. So here we are, we've just gone over a list of things that could go wrong, okay? When it comes to using this methodology of training models with examples and then using that model to do further predictions, right? We saw a list of things that could go wrong, and it's indeed a depressing list because it looks like there are many things that can go wrong. On the other hand, you know that AI has been used to solve many problems in real life. In fact, we ourselves looked at the binary linear classifier and the linear regression models, which give us a fairly good accuracy in terms of, predicting future inputs. So where does the truth really lie? We need to jump into the theory that we've been talking about and find out how we can navigate our way around these things that could possibly sink our boat. Okay. To do that, I need to introduce certain terminology. Okay, we need to start introducing some formal terminology. So far, I have been using colloquial language. I've been using language from day-to-day life to explain, what these models are and so on and so forth. But if things are going to get a little bit more mathematical down the road, we better have a formal terminology. So I want to spend some time on certain definitions and certain terminology, like I said. So let's get started. Okay, this is a diagram that you've been seeing all the time. You have inputs, you have an unknown process, and these inputs result in certain outputs. Okay, this unknown process that you are trying to model can be viewed as a function. Okay, as a function from x to y. Right? So this function takes x's as the inputs, the various x's as the inputs, and for each of these x's, it results in a y. So this is really a function, and we call this a target function. A target function. Why do we call it a target function? We call it the target function because that is the function that we want to attain, or that is the function that we want to determine. And I have put a question mark over here because, like I said, it is an unknown function. There is a function, but it is an unknown function, and this function, which we call the target function, maps all the inputs x from the set x to corresponding outputs in the set y, right? So input xi will result in an output yi and so on and so forth. Okay. Probability distribution P. Okay. Now, what is this probability distribution? This is the probability distribution that governs the inputs. Okay. What do I mean by that? Let's go back to the example from a few lectures earlier, where I said that, we took an example of predicting whether people wear glasses or don't wear glasses based on their age and income, right? So the set of people that you can consider, they obviously, their ages and their incomes fall in certain range, and certain values of ages and certain values of incomes are more likely than others, right? So for example, if you were to conduct the experiment in front of a college, the age would probably be, in the late teens or early 20s. The outputs would not, the income would not be all that impressive. Whereas if you were to conduct the same experiment in front of a corporate building, you would see that the ages are slightly more and, the incomes are also correspondingly higher. So the distribution of the values that the inputs take is governed by a certain probability distribution. Not all inputs are equally likely. Some inputs are more likely than others. Inputs in certain ranges are more likely than inputs in certain other ranges. And that is what I mean by the probability distribution of the inputs. Okay. So we assume that the inputs are governed by a certain probability distribution, which we will call P. Next, what we have are training samples, okay, training examples, and I have shown them as these tuples. Tuples in the sense the training examples that we were given are x1, for the input x1 you got an output y1, for the input x2 you got a output y2, so on and so forth. For the input xn you got an output yn. Now why have, I mean, just to roll back, why have I shown x capital and y small? Because I want to indicate that this x could be a vector, right? I mean, it could, the inputs could have multiple dimensions. So I'm denoting that by a capital X, the output, a scalar, I'm denoting as a small y. So these are your training examples. Now there is a small change of notation. So far I have been using m to denote the number of training examples and n to denote the degree of polynomials in your binary classification, etc. I am making this change now to better align with literature that you may run into. Okay, so hereafter our n is going to be the number of training samples. And m will denote something else, as we will see. Okay, so there are n training examples. This is your training data that we have been talking about, and they are essentially pairs of x, y, right, denoted in this fashion. We will also define something called the hypothesis set. Okay, so what is this hypothesis set? Okay, the hypothesis set H is the set of all possible functions from x to y, and the target function is potentially a member of this hypothesis set as well. Okay, hopefully, may not be, but the hypothesis set is the set over which you will search for the function that best mimics the target function. I think that's the right way to put it. Okay, I'll repeat what I said. The hypothesis set is the set of functions going from x to y, of course. The hypothesis set is the set of functions over which you will look for a function that best mimics the target function. Okay, that is what the hypothesis set is. So let me give an example. When we were dealing with the binary classifier, we said that our output y was equal to w1 x1 plus w2 x2 plus so on and so forth, right? And the weights w's were the attributes or parameters of the model. These kind of linear equations, all of these linear equations for various values of w1, w2, etc., are actually h1, h2, h3, etc. Okay, so for certain values of w1, w2, etc., you get h1. So each of these hyperplanes, I mean, let me put it this way, each of these hyperplanes corresponds to one of these hypotheses. Okay, and remember what we did, we looked for the best hyperplane that gave us the best separation, etc., and therefore we looked for the best function h out of this hypothesis set. So to give a concrete example of what a hypothesis set would look like, the hypothesis set is the set of all hyperplanes for the in the case of the binary linear classifier example, and each function in that hypothesis set represented one hyperplane. Okay, and there was a best hyperplane that we tried to find, which we thought best mimicked the target function. Okay, so this is going to be known as the hypothesis set, the set of all hypotheses. Okay, and this set can be infinite. This set is not necessarily a finite set. Okay, all possible hypotheses over which you want to search for the target function, you can put into the hypothesis set. This set could be infinite, and you would call it your hypothesis set. Learning algorithm, we've looked at this earlier. The learning algorithm we will represent by this cursive A, okay? And what the learning algorithm does is that it takes the training samples, it trains the training samples, and then searches over the hypothesis set to find the best hypothesis, which is also called the final hypothesis. And we will represent it by the letter G, which closely mimics F. Okay, which closely mimics F. So the job of the learning algorithm is to go over this entire hypothesis set and find the best hypothesis. That best hypothesis we will call G, or we will also call it the final hypothesis, and this G is expected to closely approximate your target function f. Okay, so this is the notation that we are going to use, right? So for example, I will once again go back to the binary linear classifier. Your learning algorithm was basically an optimization that you set up, and that optimization went over all possible values of the weights and came up with the best weights. Okay, so that was your learning algorithm. I'll repeat the learning algorithm. What goes into the learning algorithm? The training samples that you had and your hypothesis set. Okay, so the learning we are restricting to the hypothesis set, right? For a hypothesis set, there will be a learning algorithm. For another hypothesis set, you may perhaps have different learning algorithm, and so on and so forth, right? Final hypothesis G, which is the element of H. G is the H that is the best approximation to F. Okay, so this is the terminology that we are going to use going forward. Okay, I want to now go to certain definitions. Okay, in-sample error. Okay, the in-sample error of a hypothesis on a data sample is its error ratio on the data sample. Very simple. So the in-sample error is nothing but the error that you make on your training data. Okay, and it is related to the hypothesis you choose. So the in-sample error for H1 will be different from the in-sample error for H2, and so on and so forth on the same data sample, on the same training examples. And in turn, the in-sample error would also depend upon which training data you took as a data sample. Okay, so the in-sample error depends upon the hypothesis that you that you are looking at and the data sample that you have been given, and it's simply the error ratio. Okay, so again, if I have to go back to my colloquial language, the in-sample error is the error that you make on your training data. Okay, for a particular hyperplane. Okay, in-sample error. The in-sample error is going to be denoted by this capital E with a subscript in, because it will denote the in-sample error, and it is the summation over k, where k runs over your number of samples in your training data, and this function 1 when hk is not equal to fk. Okay, what is this function 1? The function 1 basically results in an output 1 when this is true. Okay, and sorry, let me write this true. Okay, and the 1 function returns a 0 when what's in the bracket is false. So what this is saying is count the number of data samples on which your HK, okay, the output of the hypothesis, does not match the training data that you, the output in the training data, and divide it by n. This is nothing but, you know, your the percentage of error that you make on your training sample. I've just introduced some notation and some functions, right? Because we need to get into the math later. So the 1 function, like I said, is if its argument is true, it returns a 1. And if its argument is false, it returns a 0. So what this is doing is essentially counting the mismatches between the hypothesis that you have picked and what you are seeing in the training data, right? So this is the in-sample error. Out-of-sample error. The out-of-sample error of a hypothesis, the out-of-sample error of a hypothesis is the probability of error on data not in the training sample. Okay, and it's a probability because the number of test points is not fixed. Okay, we remember we moved away from this we moved away from this philosophy of having 5,000 total number of examples, dividing them into 1,000 training, 4,000 testing. It's not going to work that way. You could have an infinite number of test points that keep coming. Many of the test points you may not have seen right now, as we saw in the example of predicting the stock prices and so on, right? So the out of sample error of a hypothesis is a probability. Okay, it's a probability of error on data that is not in the training samples. Okay, and I repeat, it's a probability because the number of test points is not fixed. Okay, the number of test points is not fixed. This we call the out of sample error. So far in our colloquial language, we have been referring to it as the error rate on the test inputs, right? But we want to move away from the test input business, because what is out of sample could essentially be infinite or very large, right? So that's why we are now going to call it the out of sample error, the error probability on a input that is not in the training sample. How do we define it? It's a probability, okay? Probability of your hypothesis not matching the target function for any inputs that are not in the training sample, out of sample inputs, right? And this is actually equal to E. This E actually stands for expected value. Expected value, as you know from probability, for those who have studied a little bit of probability, you know what expected value is. Expected value is really like the mean, right? Of this function 1 when hx is not equal to f of x, okay, for data outside the sample. The fact that this is equal to this is an exercise that I will leave for you. The proof is literally 2 lines. It requires you to understand what the expected value is, and therefore I'm going to leave it as an exercise. Okay, so error out of sample error, E out is a probability. Okay, and it is the expected value of this 1. I told you what this function 1 is, of hx not equal to fx on data that you have not seen, right? So this is the out of sample error. Important terminology. Let's move on. Generalization. Okay, generalization is a word that you will run into. Extending the in-sample performance of an hypothesis to out-of-sample inputs is known as generalization. Okay, so the way this word is often used is how well a hypothesis generalizes. Okay, when you say how well a hypothesis generalizes, you are essentially saying how closely a hypothesis mimics its in-sample performance on out-of-sample data. Okay, so when let's say the error in EIN is equal to E out, right, the red blocks that we saw in the earlier slide, when EIN is approximately equal to E out, we say that that hypothesis generalizes very well. Okay, and if E in and E out are vastly different, you will say that the hypothesis does not generalize very well, right? So if your in sample error is like 0.1% and your out of sample error is a disaster, 80% of the out of sample error was like 80%, you say that, hey, look, this particular hypothesis did not generalize very well. Okay, so this is a word that's is going to be used very often, right? So I want to state exactly what it is, right? And you normally talk about generalization in the context of a hypothesis, right? It could be your final hypothesis, it could be not something that is your final hypothesis, but generalization is usually spoken about in the context of a hypothesis. That's generalization. Verification. The process of checking the out of sample performance of a hypothesis. So you came up with a hypothesis, it gave you certain accuracy on your training data, and then you went ahead and started checking its performance on out of sample data, right? That exercise that you would be doing would be called verification. So verification is performed to check how well a hypothesis generalizes, right? So I'm trying to sort of link these terms with each other. Verification is performed to check how well a hypothesis generalizes. Verification is basically, in colloquial language, testing the performance of your model on test inputs, right? That's verification. You may think that I'm just repackaging things that we've already learned into, with new words, and partly that is true. But since we are serious students of this topic, we need to align our terminology with what serious researchers use. Okay, so that's the reason I'm sort of giving you these terms. Moving on. Overfitting. Overfitting is when a hypothesis tracks the patterns in the sample too closely. Now there is a little bit of subjectivity here because I use words like too closely. What the hell do I mean by too closely? We will see. But in general, when your hypothesis captures the patterns in your sample very closely. Remember in that example that I showed drawing that really curved line, that is known as overfitting. And underfitting is when your hypothesis does not capture the patterns in the sample as much as it should. Okay, again being a little bit subjective, but in other words, overfitting is when you take your training data very seriously, and underfitting is when you do not take your training data adequately seriously. Okay. In overfitting, your model fits the hypothesis very well. Your model or your hypothesis fits the training data very accurately, over accurately. And in underfitting, you're sort of not doing it to the extent you should. Okay, so overfitting and underfitting are two other terms that will be thrown around liberally. Regularization. Okay. Regularization refers to techniques that modify the hypothesis set or modify the learning algorithm to reduce overfitting and improve generalization. Okay, this is a definition that I have tried to squeeze in all the terms that we just learned about. So let me repeat. Regularization are techniques, okay, so things that you do that modify your hypothesis set or your learning algorithm. So either they tweak the learning algorithm or they modify your hypothesis set, in the sense you will throw out certain hypothesis, or you may add certain hypothesis to your hypothesis set, etc. Okay, so you can modify the hypothesis set or modify the learning algorithm. And the purpose of regularization is to improve generalization. Improve generalization means try to make sure that your out of sample performance mimics your in sample performance. Your E out is relatively closer to your E in. Okay, and that typically happens when you reduce overfitting. Now this is extremely intuitive, but I'll show you with an example. Okay, let's go back to this example in case you've not understood this, right? I mean, we said that you could have a hypothesis like this, or you could sort of have an hypothesis that went like this, capturing every single nuance of your training data, right? Okay, so we also said that if you had a hypothesis like this, I mean, if you had a very high order polynomial, now this curve would typically be a high order polynomial. If you had this kind of a curve, if you came up with this kind of a hypothesis to separate your two classes based on the training data you have given, something intuitively tells you that you have overfitted to the training data, right? So this is an example of overfitting. And like we said, suppose if these red dots turned out to be yellow, you would be making a lot of error on your out of sample data whereas your in-sample error was 0, right? Very low in-sample error, but out-of-sample error could be substantial. So when you try to do overfitting, your in-sample error and your out-of-sample error could be vastly different. Your output sample error could be much worse than your in-sample error. Whereas if you sort of did not do this kind of a curve, you just let's say created a straight line simple model to sort of differentiate between the two classes, you would be making a lot of mistakes on your training data, a fair number of mistakes on your training data, but chances are that your out of sample performance would also be roughly equal to your in sample performance, right? If I just drew a straight line. So all I'm saying is that when you do not try to overfit, your hypothesis is generalizes better. Okay, if you try to overfit, if you're overfitting too much, your hypothesis will not generalize as well. In other words, your E out and E in will be vastly different, right? And if somebody told you that, this is my hypothesis, this curved thing is the hypothesis that I'm going to use, and your friend comes along and tells you that, hey, look, let's not go with this curve, let's go with something, that's a little bit more, let's go with the straight line, for example. He is trying to regularize your hypothesis so that the out of sample error mimics the in sample error, right? So I have introduced a bunch of terminology, but I think I have tried to sort of link it all together so that it makes sense. Okay. Just putting in words on the slide what I just said. In case of overfitting, the hypothesis does not generalize well. Okay, in case of overfitting, where you are following the training data far too closely, that particular hypothesis does not generalize well. Conversely, if a hypothesis does not generalize well, it is likely to have overfitted the data, okay, and it needs regularization, right? So the converse says that if your hypothesis does not generalize well, in the sense that if E out and E in are vastly different, you've probably overfitted the data, okay, and you need to sort of regularize your hypothesis or your learning algorithm so that the difference between E out and E in is reduced. Okay. In case of underfitting, the hypothesis gives higher than possible in sample error. Okay. So in case of underfitting, you are taking a hit on your in sample error. Okay. Your in sample error is higher than it could have been for a commensurate reduction in out of sample error. Okay, so I don't want a situation where my out of sample error is a disaster and I have my in sample error is really, really good. I would rather take a hit on my in sample error so that my out of sample error is a little bit better, right? So that's what underfitting would do. And like I said, these are subjective terms, overfitting and underfitting, but they indicate what is happening. And this is the balancing act that lies at the heart of the theory of learning. Okay. And it again goes down to what we said in one of the earlier slides. All of this has to do with how seriously you take the training data, right? Okay. So we are moving now to terminology that is a little bit more formal. We've spent time on seeing what can go wrong when it comes to learning. We've looked at some terminology, definitions, etc. And having done that, let's go back to the question that we were asking, that we were talking about. Is learning possible? Right? So here is what we have learned. Learning is not possible for a random process, right? I mean, if you had a random number generator, no amount of input and output training data is going to help you. So is learning possible? Not for a random process. We also saw that learning is not possible for every combination of problem, hypothesis set and n. Well, number of samples, we changed that to n, right? Sorry, let's stay uniform with our notation. So we saw certain examples which were obviously manufactured examples of problems where the hypothesis set or the hypothesis that you ended up with could vary depending upon whom you asked, or you just felt that the number of samples was not adequate, right? So learning is clearly not possible for every combination of problem, say of a problem, hypothesis set and n. In other words, given a problem, given a fixed hypothesis set and given a fixed number of samples, learning may not be possible. Right? I mean, like I said, you could have multiple polynomials, higher order polynomials passing through certain number of training points. Right? And yet, as we know, AI techniques are employed on many real life problems. Right? So let's address this dichotomy now. We know that learning is not possible in certain cases, but yet AI techniques are employed on real life problems. So why? I mean, what lies beneath this? Let's see. Okay, here is a reality check for us. A reality check. Okay, so here is the reality. AI deals with problems that occur in real life. Okay, solving real life problems. Okay, and what is it about real life problems? What is it about real life problems? In real life problems, data comes from measurements of physical processes or laboratory readings or observations of real life behavior and so on. Okay, so it isn't as if there is an evil person sitting somewhere and manufacturing data in real time to trick you. I mean, the examples that we saw where learning is not possible, it was clear that all of those examples were manufactured data, right? Manufactured examples, and they were manufactured specifically with the aim to trick you. But that is not the case in real life problems. There's nobody who's sitting there trying to manufacture data to trick you. Of course, there will be deviations in data. Of course, there will be patterns that you may not catch. All of that is true, but it is not a case where somebody is actually manufacturing the entire data in order to send you on a wrong path. Right? So data comes from measurements of physical processes, laboratory readings, and observations of real life behavior. Right? So this is what reality is. These are the problems that AI is typically confronted with. So it's time to reformulate our question. The question of is learning possible? It's time to reformulate that question. And how are we going to reformulate it? We are going to say that the in-sample and out-of-sample data both come from the same probability distribution. Okay, so it is not as if your training data has come from some other probability distribution of X and your out-of-sample data has an entirely different probability distribution. That's not going to be the case. We are going to specifically deal with the situation where in-sample data and out-of-sample data come from the same probability distribution X, right? The P that we saw. I'll go back to that slide in a moment, right? So they both, this is a fair assumption. They're fair assumption. Nobody is expecting you to train the model on data that comes from a totally different probability distribution from what you will subsequently encounter. So, number one. Number two, we will control n, which is the number of training samples. Okay, we will control n. It's not as if somebody will tell you this is n and that's it. If you need more training data, you can ask for it. And again, this mimics real life, right? I mean, in most cases, you have essentially infinite out of sample data. And if you ask for, instead of polling 500 people, if you wanted to poll 2000 people to get a better election prediction, nobody is going to say that you cannot poll 2000 people. You have to poll only 500 people. So you control n. Number of training samples, you can always ask for a little bit more if you need them. Right? So this is the second assumption that we will proceed with. And thirdly, this is the most important. We are going to make a mental change. Okay, a mental change. We are going to change this question. Is learning possible? Is learning possible? We are not going to ask this question. We are going to ask the question, is learning probable? Okay, so instead of this word possible, where you can create some manufactured negative examples, we are going to ask the question, is learning probable? Okay, so we are going to appeal to probabilities. We are going to appeal to what is normally expected to happen. We are going to sort of go with the assumption that we are going to solve real life problems by and large, right? And therefore we will now ask the question, is learning probable? Okay, we are going to think in terms of probabilities. So these are the changes that we are going to do and sort of reformulate the question that we have been asking, right? Okay. Okay, now there is only one thing that matters, okay, and I have a slide for it. E out is the only thing that matters, which is the expected value of out of sample error, which is the probability that your hypothesis does not match the target function on an out of sample data. Okay, E out is the only thing that matters. Nothing else matters. E in does not matter. Nothing else matters. Hypothesis set, your training algorithm, all of that can change. It's all in your hands. The only thing that you need to focus on is E out, right? If you need to stop this video here for a moment, please do, because this is worth understanding, worth spending a moment on. E out, which is the error, out of sample error, is the only thing that matters in all of your AI work, right? Okay. And therefore, we will now start using a different definition of learning, right? I mean, our earlier definition of learning had that had the input, output, and unknown process, etc., etc. Let's sort of reformulate our definition of learning. Okay, make it a little bit more precise. And I propose that learning is the process of using the training samples to influence, which is reduce. I mean, typically we want to reduce E out, the out of sample error. Okay, I'll repeat. Learning is the process of using training samples to reduce E out. E out is the only thing that we care about, and the only thing that we want to do is use the training samples to reduce E out, and the process of doing that is what we will call learning. Okay, so we have introduced E out, which is like a mathematical quantity, into the definition of learning. Right? Okay, let me go back a few slides. Okay, let me go back a few slides to where we were. Give me a moment. Okay, I'm going to go back to this slide. Okay, so we said a number of things. The first thing we said that the probability distribution that drives the overall inputs, your training samples are picked up from the same probability distribution. An assumption that can be, can be fairly made in real life, right? So your training examples are also driven by the same probability distribution. The second assumption that we made is the number of points in the training data, the N. The N is something in your control. You can ask for more training data if you need it, and therefore the size of your training sample set is your in sample size can be larger than, you can make it larger or smaller, right? And finally, very importantly, your final hypothesis G, okay, G is going to be the final hypothesis that you search for your learning algorithm and your hypothesis set, etc., etc. The final hypothesis that you will come up with is, the final hypothesis that you come up with is going to approximate the target function on out of sample data, right? So outside your training samples, right? So your final hypothesis should be such that it approximates the target function as well as possible on out of sample data, right? When think about an analogy here. If your kid is sort of appearing for his 10th standard or 12th standard examinations, it absolutely does not matter what his performance was in the prelims or in the practice tests that you gave him, right? I mean, he could have done disastrously on those, you don't care. What you care about is how he does on the final exam, right? Similarly, how your hypothesis performs on the training samples is not as important or is insignificant, I will say, in terms of, when compared with how well your hypothesis performs on out of sample data. Now, of course, there is an argument to be made that since the training samples come from the same probability distribution, therefore your E in is going to closely mimic E out, etc., etc. Those are details. But right now, all I am saying is that E in is not a consideration. E out is the only quantity that you are going to be concerned with, and therefore the final hypothesis that your learning algorithm comes up with has to be such that it mimics the target function on out of sample data. Okay, great. Let's go back to where we were. Sorry, I need to scroll through all these slides. Let's go. Okay, here we were. Great. So E out is what we are concerned about, and the entire exercise over the next few lectures are going to be concerned with how sort of you reduce E out, because that's your objective, right? That's the objective of learning. Okay, now if you want to get a handle on a quantity, there are some ways to go about doing it. I mean, if you have direct insights into this quantity, it's great. But typically what you would do is you would try to sort of break it up into its components, perhaps factors, right? Or perhaps into its additive components, right? You would try to break it up into its additive components. Any quantity that you want to that you want to analyze, that you want to influence, you want to obtain an insight in, the typical way of doing it is to find out what goes into E out. Okay, what goes into E out, and then maybe you have better insight into these quantities individually, right? And by controlling these components, perhaps you can control E out, right? You get this, right? So we are not going to factorize E out. We are going to sort of break it up into additive components. Okay, that is what we are going to do to get a handle on E out, and therefore understand what goes into E out, and therefore influence the value of E out. Okay, so we are going to sort of deal with decompositions of E out done in order to minimize E out. Okay. Okay. This is just what I said. It's logical to explore what contributes to E out. One way to do it is via its decomposition. I think all of us agree on it. There are two theories. In the theory of learning, there are two theories to decompose E out. Okay. So people have gone exactly down that path. They have tried to break out, what contributes to E out. They have tried to decompose E out. And there are two separate theories, two standalone independent theories of decomposing E that allow you to decompose E out. One is called the PAC theory, probably approximately correct. PAC stands for probably approximately correct. Okay. And in this theory, what is shown is that E out is less than E in plus a certain quantity with probability greater than 1 minus delta. Okay, so I am sort of jumping ahead of myself here, and I will tell you why I am doing it. But I am telling you upfront that there are two theories or two ways in which to decompose E out. One of the theories is called probability approximately correct approach, where E out is decomposed as E in and another quantity. Okay, and this mysterious quantity, as you can imagine, is going to be a function of delta. The PAC theory says that this is valid with a probability higher than 1 minus delta. Okay, so this quantity Q is going to be a function of delta. It's going to be a function of number of training samples, and it's going to be a function of what is called the complexity or capability of your hypothesis set. Okay, we are going to spend 2 hours discussing this, but I'm just laying this out in front of you. Okay, so this is one way of decomposing E out, right? And we are going to study this PAC theory in detail, and it's going to take us through terms like, we will deal with Hövding's inequality, we will talk about growth function, we will talk about shattering, we will talk about VC dimension, and then finally we'll talk about the generalization bound. All of these come under what's called the probability approximately correct theory, PAC. Okay, there is another way to decompose E out, and that is called the bias-variance theory, where E out, you will see, can be decomposed into 2 things called bias and variance respectively, and then we are going to try and see how we can control the bias and variance, right? Okay, so I am right now laying the roadmap for the next 2 or 3 lectures. Okay, I am laying out the roadmap. This may seem a little bit confusing now, but I'm going to tell you, I'm telegraphing what's going to come later. And that always helps, right? I mean, you may have visited a park, or you may have visited a zoo, and right at the entrance of the zoo, they show you what the layout of the zoo is. And if you go down this path, you will see elephants, you will see a giraffe, you will see a hippopotamus. And if you go down that path, you will see some lions and tigers and so on and so forth, right? And then they have a dot that shows you are here. So let me draw a dot. You are here. Okay. You are here. And the zoo that we are going to explore has 2 paths. Okay. This one path is called the PAC path, and that is going to decompose E out in this mysterious fashion. I don't want you to understand, I don't expect you to understand or figure out what these things are, etc. at all. I'm just giving you a map, a road map. Okay. So this path will take you down this sort of a decomposition, where you will meet animals like the Hövding inequality, the growth function, shattering, VC dimension, generalization bound, and so on and so forth. So these are the things that you will see when you go around on this particular path. And when you go on this particular path, you are going to meet these 2 animals called bias and variance. Right? So these are 2 theories on how you decompose E out. And once you decompose E out, then you worry about how you can control the individual factors or individual terms in this decomposition. Right? Okay. Now, because the PAC theory is, it's not easy. It's going to be fairly mathematical, but this is the path that we will that we will take. We will do this as is typically done for the case of binary classifier. Okay, binary classifier. So all the derivations, etc., that we will do along this path will be for the specific case of binary classifier. Those can be extended to other problems, but that would be beyond the scope of this particular lecture series. They are a little bit more complex than we can handle at this stage, right? So this is one path that we are going to take. We will go down this path for the next couple of lectures. It will be fairly mathematical, but you will enjoy this. And then once we have touched down this path, we will make way back to where we were, and we will go on this path and see the animals that are out here, right? So that is the roadmap for our next 3 lectures, 3, 4 perhaps. Okay, now here is something that we should know. I mean, although these are 2 separate theories, they broadly offer similar prescriptions for the hypothesis set, the learning algorithms, so on and so forth. Okay, so the training samples and so on and so forth. So it's not like these are 2 different theories that have conflicting prescriptions. They broadly come up with the same prescriptions, although they are completely 2 standalone theories, and that it will be interesting to see how their prescriptions are basically pointing in the same direction, right? So this is to be understood upfront. Okay, so This brings us to the end of the lecture. What I'm going to do is give you a couple of exercises and then summarize, right? So exercise 1, we saw this earlier. I want you to show that probability of this we saw in the context of E out. You can roll back a few slides. I want you to prove that probability of hx not equal to fx out of sample is the same thing as the expected value of this function 1 whose hx not equal to fx, right? I defined what this function 1 was earlier. It's a two-step. It probably should take you just 2 lines to prove this. If you can do it in 1 line, good for you. But I hope everybody knows what expected value is. Expected value for discrete variables is simply summation xi into probability of xi, right? And for a continuous variable, this is equal to integral over x p of x dx, right? So that's what the expected value is. So go back to your probability book if this is still hazy for you. But the first exercise is for you to prove this thing, right? Like I said, it's a 2-line proof. Good for you if you do it in 1 line. Great. Exercise 2. Okay. Now, I said that in the PAC theory, we are going to demonstrate that E out is upper bounded by E in plus a mysterious quantity, which is a function of delta n and the complexity or the capability of the hypothesis set. This I have not defined at all, right? And we said that this we will show happens with a probability of 1 minus delta, where delta is any small number, right? So of course Q depends on delta, it depends on n, so on. So it depends upon the hypothesis set that you choose. You can possibly think that taking a neural network as your hypothesis set will give you a different Q from just using a linear classifier, right? So this is what the PAC will show. Okay. Now, without any understanding of what this Q is, in fact, without any understanding what this CH is, except the vague notion that CH captures the complexity of the hypothesis in the hypothesis set, can you guess the behavior of the function Q, whether it increases, decreases or independent with respect to delta n and ch? Okay, so I'm completely jumping ahead of myself, but I think these exercises are important to do. You know, I mean, even given what you know, being able to giving it some thought, trying to predict the behavior of function with respect to its arguments is a very worthwhile exercise. And then if you go wrong, there's no problem. That's quite fine. You will stand corrected when we go over the lectures. But it's always a good idea to explore something before knowing what it is, right? And that's the reason I want you to spend 5 minutes imagining what the behavior of the function Q is likely to be with respect to its arguments, right? I will spend a minute on CH. CH is a quantity that has not been defined, but vaguely consider it to represent the complexity of your hypothesis, of the functions in your hypothesis set. Neural networks versus linear versus polynomial, etc., 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 right? And remember, this is a bound, this quantity Q is an additional quantity. It's an additional quantity in addition to E in, right? So E in you would know. And I don't want you to tell me how E in behaves or how E out behaves with respect to these, right? I mean, they also will depend on these. What I want you to tell is to guess is how this additional quantity Q will behave, right? So requires a little bit of deep thought, but I think you are up for it. Great. Let's move on. Summary. This brings us to the end of the first lecture. Okay. We addressed the question of what is learning. In fact, we began with one definition and then modified that definition as we went along. We addressed the question of is learning possible, And we said that we would answer this question probabilistically rather than definitively. We would address it in terms of probabilities, what is likely to happen, right, in real life, right? And finally, we stressed the importance of E out, and we said that E out is the only thing that matters. It's the key. And we are going to study theories which allow you to estimate E out and thereby control E out, right? So this is the summary. This was an overview session. Even though it was an overview session, I sort of gave you a preview of what is going to come in the next 2, 3, 4 lectures. We would deal with the PAC theory, we will deal with bias and variance, and I also showed you the paths that we would take to get there. This is simply a precursor to get you mentally ready so that the next lectures don't come to you as a surprise, right? So in the next lecture, what you're going to study, you already know, right? And you can be sort of mentally prepared for it. I also gave you a couple of exercises to sort of allow you to jump ahead of where we are and chance your hand at guessing what that quantity Q and what that quantity CH is likely to look like, right? Okay, great. So that is it. That's the end of this lecture. The next few lectures are going to be more mathematical, as you can imagine, but I am 100% sure you will enjoy them. Thank you. Goodbye.